So we're seeing here, right? Everybody can see clearly, hopefully. So we can see here that the titanium ion, right, is a transition metal ion, right? So we know that our period 3 transition, well, period 4 transition metals tend to have colored ions, right? So where does the color come from? We note that within transition metals, right, we tend to have d orbitals. So let me just use these 4 lines right here to just show our d orbitals, right? Now these d orbitals, this is not specific to titanium in any way, but these d orbitals have electrons occupying them. Right, so let me just write these in. So they have electrons occupying them. Right? Fine. Fine so far, guys? Alright. So they have electrons occupying them. Now, when we have electrons being lost, right? For example, here we have electrons being lost. We end up with an empty orbital. Now let's look what happens. When there's an empty orbital, we tend to have now the creation of what we call degenerate orbitals. So these orbitals are on different energy levels. Following? I hope everyone's following, right? So they're on different energy levels. So we note this. And this would just be one spin there. Alright? So they're on different energy levels. Now the presence now, when we have ions, transition metal ions, they tend to form complex ions, right? So we have the presence of ligands. So we know that ligands are these type of usually, well, sometimes they are usually basic compounds, right? They donate electrons to these positive transition element ions, right? So they create these complexes. So these orbitals, right? So these complexes causes the orbitals to come close, right, to the ligands, right? And they're pushed into slightly higher energy levels. That's why you see the one with the slightly higher energy level here, right? So it pushed the ones with slightly higher energy levels, right, further away. And it splits the orbitals into 2 groups. So we have degenerate orbitals being formed. So that's what we have here. Now, when an electron from a d orbital of a lower energy level moves into the presence of a higher energy level, now that electronic transition between degenerate d orbitals, right, will have to happen due to contribution of some light. So let's say that this electron gets promoted, right? Let's say that gets promoted and it gets moved up here, right? Now, we generally know from module 1 that this only occurs if light is introduced, right? So let's say that light is introduced to the system. So you know that this is called photoexcitation. So when the photons of light actually excite, right, or give some amount of energy to the electrons, right? So it causes the electron to absorb energy and move into these degenerate orbitals, right? Fine. We're following? Hope we're following.
Yes, sir.
All right.
Thanks.
So we have this here. So this is what we call the absorption of energy. So the energy is absorbed by the electron gets excited and it jumps up to a higher energy level. Now this wavelength of light here is at it is at a specific wavelength, right? So it's at a specific wavelength. Note that, right? So it's at a specific wavelength. We have to note that the energy generally of this, right? So delta E is going to be equal to the Planck's constant times the frequency. So we know that equation. We know that about the light. Now, this electron, although energized, won't exist in this degenerate orbital forever. Right? So it's the same thing like when somebody gets excited. Let's say that somebody starts laughing, right? You won't laugh forever. You won't continue to be in this excited state, right? So what tends to happen is that this electron now will actually move down back into its lower energy state. And this loss of energy, right, allows for the light that was initially absorbed to be emitted. Right? That is what we call emission. So when we have light entering, it is absorption. And when we have light leaving, that is called emission. Fine so far. Now, remember from module 1, Cape Chemistry 1 students, you have to remember that. Energy is quantized, meaning that the amount of energy absorbed will be equal to the amount of energy emitted. We remember that?
Yes.
All right. So this means that if it is generally the same, it is quantized, right? That means that the wavelength, right, of light that is of the initial photon that came in, right, that is absorbed, will actually put out actually a different wavelength at this time. So it's going to be the same energy but a different wavelength, right? Or, well, let's not say it's a different wavelength. Let's say it's the same wavelength, right? But it shows a different thing other than just it being clear. So before all of this happens, before everything starts showing light energy, right, and well, showing a color, right, this is what happens, right? Absorption, right, in the lower d orbit, degenerate d orbital, right, moving the electron to a higher state in a higher degenerate d orbital. When it returns to its state, now it emits light. Now this light here, specifically for the titanium that we started off talking about, this light is shown, can be shown on a graph, right? So remember the spectrum, right? So we should remember the spectrum. So the spectrum works off of different wavelengths specifically, right? So let's say that there is around 400 nanometers, right? Around 500 nanometers, 600, and around 700 nanometers. So all of this is in nanometers, right? And let's just show an imaginary wavelength, right? What we have to note is that each of these wavelengths, let me write this properly, each of these wavelengths correspond to a different range of light. So let's say around 400 is violet, around 500 is a greenish light, around 600 is yellow, and around 700 is red. So what we're saying is that the light emitted from the electron losing its energy and falling back to a ground state, that light has a wavelength that corresponds with the wavelength of light in the visible region that corresponds with that violet color. The question here from 2016, right, asks, right, well, are stated that titanium 3 chloride, right, has a violet color in solution. So it shows that when the electrons are moving within the degenerate orbitals, electronic transition happens within the degenerate d orbitals of the titanium 3 plus ion. It emits light that corresponds to the wavelength found in around the 400 region of the visible spectrum, giving off violet light. So this is how colors, right, are emitted from these transition ion complexes. Remember that ligands are a part of this. Remember that the ions form complexes, right? So transition elements form complex ions. So note that. So that is my explanation.